By the autumn of 1943, the Battle of the Atlantic had passed through its decisive, costly phase. Allied convoy systems, long-range air patrols, radar-equipped aircraft, improved sonar, ASDIC, better cooperation between naval and air forces, and signals intelligence had inflicted heavy losses on German U-boats. The older German submarine types, principally the Type 22 and the larger Type IX, were conceived in an era when submarines operated primarily as surface ships that submerged to attack or evade. Their underwater performance was limited. Batteries gave them only a few hours of submerged endurance at slow speeds. Hulls were optimized for surface seaworthiness rather than low acoustic signature. Snorkels were not standard, and their operational doctrine included frequent surfacing to recharge batteries and communicate. These surface habits made them vulnerable to radar-equipped aircraft and direction finding of radio transmissions. The Type 21, known to its designers as the electroboat, was a radical departure from that paradigm. Its entire conceptual framework was premised on the idea of the submarine as a true submersible, not merely a surface vessel that could dive, but an underwater ship whose primary operating mode was submerged. That shift in operating philosophy had immediate and profound implications for detectability. Detectability in the maritime domain depends on multiple physics and technology-driven factors: radar cross-section and exposure above water, thermal, acoustic, and hydrodynamic signatures below the surface, the electromagnetic emissions produced by crude radioactivity, and tactical behavior that creates exploitable patterns. The Type 21 attacked those factors from multiple angles: hydrodynamic streamlining to reduce flow noise and wake, vastly increased battery capacity to reduce the need to surface, snorkel integration to allow diesel operation at periscope depth, electrical propulsion optimized for submerged speed and quiet running, and a hull form that minimized surfaces and protrusions that would reflect radar or create turbulent wakes. Each of these design choices matters on its own. Together, they altered the detection calculus in ways that Allied ASW systems were not fully prepared to counter. Start with the hull and hydrodynamics. Traditional U-boats of the early war years had hulls optimized for the surface, pronounced deckhouses, conning tower structures, and appendages that increase aerodynamic and hydrodynamic drag but provide useful surface performance. When moving submerged, these shapes produce turbulent flow and cavitation around propellers and control surfaces. Turbulence means noise. Noise is what passive sonar and hydrophone arrays hear at ranges that depend on ambient noise and propagation conditions. By improving blade shape, using larger diameter screws turning at lower RPM for the same thrust, and by careful attention to hull-propeller interaction, the designers reduced the signature. From an Allied sonar operator's perspective, a teardrop hull with low cavitation propellers simply sounded different and quieter than the older U-boats. Battery capacity and electrical propulsion were another cornerstone of stealth. To evade radar and HFDF, a U-boat ideally wants to remain submerged for long stretches. Pre-Type 21 boats relied on lead-acid battery banks sized for a few hours of submerged transit at low speed. Attack tactics often required surfacing at night to charge batteries and to gain speed. The Type 21 carried a much larger battery capacity, a design priority. Larger batteries translated to longer submerged endurance at cruising speeds and to the ability to sprint at higher underwater speeds without immediately draining power. This meant that Type 21 commanders could choose to stay submerged even during periods when older boats would be forced to surface, thereby reducing exposure to air patrols and airborne radar.
That last point matters because earlier submarines, when trying to evade a contact, suffered a dilemma. They could operate underwater, but only at slow speeds, which made them vulnerable to being outrun or boxed in by escorts. Or they could surface and run at high speed to escape, which exposed them to radar and air attack. The Type 21 softened that dilemma by allowing higher underwater transit speed. A submarine that can transit submerged at, for example, the mid to high teens in knots, reduces the need for risky surfacing and complicates escort tactics designed around limiting submarine escape routes. High underwater speed also affects Doppler and active sonar characteristics. A fast-moving submerged target produces different echo patterns and may force sonar operators to adjust processing techniques. Airborne detection had been one of the Allies' most effective tools. Radar-equipped aircraft, first with metric radar and increasingly with centimetric radar later in the war, could detect a submarine's conning tower, radar reflectors, or even periscope wake at night and in bad weather. The Type 21's reduced above-water profile and the tactical doctrine of remaining submerged minimized time in the air detection window. When a Type 21 did need to run its diesel engines, it could do so at snorkel depth using the snorkel mast, a device that allowed combustion air intake and exhaust removal while the hull remained mostly submerged. The snorkel itself was not a perfect solution. Its mast could be seen by radar or detected by radar returns off the masthead, and snorkel-induced engine noise and exhaust plumes could be traced. But compared to fully surfacing to charge batteries, snorkel use was a step change in exposure reduction. Considering Allied radar coverage and long-range patrol aircraft, the ability to operate diesels at periscope depth instead of on the open surface increased survivability. Acoustic discretion also arose from the Type 21's electrical architecture. Older boats used diesel engines for speed and for battery charging. Electrical propulsion was secondary and used only submerged. Switching between diesel and electric modes created mechanical noises, engines cranking, clutch engagement, rudder and shaft vibrations. The Type 21's propulsion system was designed with quieter gearing, better isolation mounts, and motor configurations that allowed smooth transitions and less mechanical noise during normal operations. The crew's acoustic signature, machinery, generators, compressors, was managed better than on older boats. Quiet machinery yields a smaller detection range for passive sonar. Since passive detection relies on picking up noise above ambient sea noise, lowering machinery noise shrinks the radius at which the submarine can be heard. One of the less obvious but crucial design aspects was sensor and communications discipline. Detectability is not only about how an object looks or sounds, it is also about what it broadcasts. Allied HFDF networks and signals intelligence had used radio transmissions to triangulate U-boat positions. The Type 21 doctrine stressed radio silence and the use of encrypted short transmissions or alternate communication methods that reduced HF exposure. In short windows when communication was unavoidable, commanders could use the radio in bursts at prearranged times and use the boat's improved submerged endurance to remain under during listening windows. The combination of long submerged endurance and disciplined radio use limited the opportunities for Allied HFDF to obtain actionable bearings. But the Type 21 stealth was not purely passive. It also included changes in shape and operational systems aimed at active warfare characteristics that indirectly reduced detectability. For example, the boat's armament focus shifted to torpedo salvo capability and faster reloading systems, meaning less time on the surface for preparing attacks. The Type 21 could carry larger torpedo loads and reload internally faster than earlier boats, reducing the need to surface to manage torpedo handling. Less surface activity equals fewer radar contacts and fewer exploitable windows for aircraft.
Finally, it is important to understand the role of industrial and technological timing. Much of the Type 21's stealth advantage derived from being conceptually and physically novel at a moment when Allied ASW doctrine had evolved to counter older U-boat behaviors. The Allies had built procedures, sensors, and tactics that were effective against surface-running, snorkel-rare submarines. The sudden introduction of a submarine specifically built for prolonged submerged operations posed a detection problem that required doctrinal and technological adjustments. Detection systems tuned to expect certain noise signatures, to watch for periscope wakes during known surfacing times, and to prioritize radar contacts at particular ranges, suddenly had to adapt to a quieter, more underwater-focused opponent. That temporal asymmetry, innovations arriving faster than countermeasures, is a classic wartime phenomenon. The Type 21 did not have to be invisible to be effective. It merely had to be harder to detect within the existing Allied detection framework and to exploit operational windows where Allied coverage was thin or where detection methods were less effective. That is precisely the engineering and tactical goal. Make the cost of detection higher and the time to react shorter for the opponent. In many cases, the Type 21 succeeded on paper. Its hydrodynamic quieting, battery-driven endurance, snorkel-equipped diesel operation, and reduced electromagnetic and above-water profile combined to produce a submarine that, if it had been deployed in numbers and under optimal crew training, would have forced Allied ASW into a more difficult, uncertain fight. However, this is only part of the story. Design features that reduce detectability can be mitigated by countermeasures, and operational realities, crew training, production problems, material shortages, and the timing of deployment all affect how the theoretical advantage translates into practice. The Allies' evolving ASW network was not static. Radar sensitivity improved, airborne depth charge patterns were refined, convoy escort tactics adapted, and sonar processing improved. Those adjustments would influence whether the Type 21 stealth translated into survivable patrols and successful attacks. The next parts of this series will examine the Allied detection capabilities of late 1944 to 45 in detail, analyze the specific gaps that Type 21 exploited, and then look at wartime case studies and the post-war legacy that shaped submarine warfare for decades. To understand why the Allies struggled so much to detect, track, and neutralize the Type 21, one must first understand just how radically this submarine differed from everything that had come before it. The Type 21, often nicknamed Electro boat, wasn't just another model in Germany's long line of U-boats. It was a total rethinking of what a submarine could be. Before the Type 21, submarines were effectively surface ships that could dive temporarily. They spent most of their time above water, recharging batteries, and traveling to target areas, only submerging to evade or attack. The Type 21 changed that dynamic entirely. It was designed to live under the surface, to be, for the first time in history, a true underwater predator rather than a submersible surface vessel. This distinction may sound subtle, but it transformed naval warfare. Earlier U-boats, like the famous Type VII or Type IX, were relatively easy for Allied sonar and radar systems to detect. These boats rammed their diesel engines on the surface, producing heat, noise, and radar reflections that aircraft could pick up. They could submerge only for limited periods, maybe 8 to 12 hours, before battery power ran out. Once that happened, the boat was forced back to the surface to recharge, becoming a visible, noisy, and vulnerable target. The Allies learned to exploit this cycle, using radar-equipped aircraft and destroyers to patrol the Atlantic. By 1943, the wolf packs that had terrorized Allied convoys were being annihilated by advanced anti-submarine tactics, long-range aircraft, and sophisticated sonar known as ASDIC. The U-boat arm was bleeding to death. Then, in the middle of this desperate situation, German engineers began quietly working on a radical solution. The Type 21 would turn the submarine from prey back into predator. The man most responsible for this concept was Helmuth Walter, a brilliant engineer who had already been experimenting with hydrogen peroxide-fueled turbines for ultra-fast submarines. Walter's ideas inspired the Kriegsmarine to rethink submarine propulsion and hull design from the ground up. Though his exotic high-speed Walter boats never entered mass production, their design philosophy deeply influenced the Type 21. Make it hydrodynamically sleek, electrically powerful, and capable of spending nearly all its time underwater. The result was revolutionary. The Type 21's streamlined hull resembled a modern nuclear submarine, far more than any wartime U-boat. Gone were the sharp angles, deck guns, and bulky conning towers that created drag and noise. Instead, the hull was smooth and hydrodynamic, allowing the boat to slip silently through the water at unprecedented speeds. Under electric power, it could cruise submerged at around 5 to 6 knots for days, or sprint underwater at a staggering 17.2 knots for short bursts. To put that into perspective, Allied destroyers could barely reach 20 knots, while submerged submarines before the Type 21 rarely exceeded 7 knots. Suddenly, the hunters of the Atlantic found themselves facing prey that could outpace their detection systems and even escape pursuit. The power plant was a masterpiece of engineering for its time. Two large diesel engines, used only when surfaced or snorkeling, charged a massive array of batteries, nearly 3 times the capacity of the previous Type IX sea boat. This enormous electrical reserve allowed the submarine to remain underwater for 2 to 3 days continuously without surfacing, something no other wartime submarine could do. Using a new snorkel system, it could even run its diesel engines while remaining at periscope depth, drawing in air through a retractable mast. This meant the submarine no longer had to surface fully, eliminating one of its greatest vulnerabilities. But stealth was about more than just staying underwater longer. German engineers understood that sound, not visibility, was the submarine's true enemy. The Allies had perfected sonar systems that could detect propeller noise, hull echoes, and even the rhythmic hum of an electric motor. So the Type 21 was designed from the start to be whisper quiet. Its electric motors were mounted on rubber bearings to reduce vibration, and the propeller was reshaped for smoother, quieter rotation. Internal machinery was soundproofed, and the hull was coated with a special rubber-like material designed to absorb sonar pulses rather than reflect them. While not fully anechoic like modern coatings, this early version of sonar camouflage made the Type 21 far harder to detect with Allied ASDIC systems. In tests conducted late in the war, Allied sonar operators struggled to maintain contact with a submerged Type 21 even at close range. The sound echoes were faint and inconsistent. Combined with the sub's ability to dive deeper, down to about 500 feet, and accelerate quickly to escape depth charges, the result was a machine that could simply vanish into the depths. In practical terms, this meant the Allies' primary anti-submarine weapons, depth charges, sonar, and radar, were all suddenly less effective. Radar couldn't find what stayed below the waves. Sonar couldn't lock onto something that slipped away faster than the sound waves could track it. The Type 21 also represented a leap in offensive capability. Traditional U-boats took several minutes to reload their torpedo tubes, forcing them to surface or remain stationary while rearming, a dangerous vulnerability during combat. The new German boat had automated hydraulic reload systems that could prepare a fresh torpedo in just 10 minutes, allowing for rapid, repeated attacks. It carried up to 23 torpedoes and could fire 6 in quick succession from its forward tubes. For the first time, a single submarine could engage multiple targets in rapid sequence, attack from deep underwater, and then vanish before anyone could react. When the Allies finally examined captured Type 21 submarines after Germany's surrender, they realized how close they had come to facing a new Battle of the Atlantic all over again. The silence of the electroboot was not just mechanical, it was historical, a quiet prelude to a revolution in undersea warfare that would shape the Cold War and beyond. If the U-boat menace of 1942 had been a storm, and the Type 21 was a shadow, unseen, unheard, and potentially unstoppable. It forced the world to confront a simple, unsettling question. How do you fight an enemy you cannot detect? When Allied forces captured Germany's last operational ports in 1945, they discovered something that sent shockwaves through naval intelligence circles. Lined up in the shipyards of Hamburg, Bremen, and Kiel were dozens of unfinished submarines, sleek, modern, almost alien compared to the boxy U-boats that had terrorized convoys just a few years before. Among them were the Type 21 and its smaller cousin, the Type 23. For Allied officers walking through the silent docks, it was a revelation. The Germans had secretly built submarines that were a generation ahead of anything the world had ever seen. And suddenly, everyone realized how lucky they had been. The immediate question was simple. Why hadn't these submarines changed the course of the war? The answer was complicated. Timing, production chaos, and the overwhelming Allied bombing campaign that crippled Germany's ability to mass-produce advanced technology. But the deeper question, the one that haunted Allied planners, was how these new submarines had managed to become so hard to detect. For the first time, the Allies faced the possibility that their dominance in the Atlantic had only been temporary, resting on not absolute superiority, but on a narrow window of technological advantage that could have closed overnight. In 1944, Allied anti-submarine warfare, or ASW, seemed nearly perfected. A vast web of radar-equipped aircraft, long-range patrol bombers, and escort carriers patrolled the North Atlantic. Convoys moved under constant protection, guided by sonar and supported by hunter-killer groups of destroyers. Allied scientists had also improved magnetic anomaly detectors, or MAD, and introduced hedgehog and squid mortars, forward-firing depth-charge systems that could engage a submarine without losing sonar contact. The ocean had been turned into a deadly grid of sensors, patrols, and mines. By every measure, the U-boat force was finished. But all of this relied on one fundamental assumption, that submarines needed to surface. The Allies' radar systems, from the ASV Mark III airborne radar to shipborne centimetric sets, were designed to catch U-boats as they charged their batteries on the surface. By 1943, these radars could spot a submarine's conning tower from several miles away, even at night. Aircraft like the B-24 Liberator and the Sunderland flying boat would swoop in, dropping depth charges or homing torpedoes. Once submerged, the U-boat only had its electric motors and limited battery power, and that made it predictable. Every sonar ping, every searchlight beam, every convoy escort was calibrated around that rhythm of surfacing and diving.
Then came the Type 21, and that rhythm vanished. To the radar operators and sonar crews who had hunted U-boats for years, the new German submarine simply broke all the rules. It could remain submerged for days at a time, move faster underwater than most destroyers could while maneuvering, and run its diesel engines using a snorkel without exposing itself on the surface. The snorkel mast was narrow, radar-absorbent, and often lost in the noise of the sea. Early Allied radar systems struggled to detect such a small target, particularly when waves and weather created natural interference. In many patrol logs, aircraft reported possible radar contact lost with no confirmation. Many of these might have been Type 21 submarines on training or transfer runs, moving silently beneath their feet, undetected. Sonar, the primary underwater detection tool, was equally outmatched. Allied sonar systems like ASDIC worked by sending out sound waves and listening for their echoes off a metal hull. This method was effective against traditional submarines, which had relatively noisy engines and a clear acoustic profile. But the Type 21's smooth, rubber-coated hull reduced those echoes dramatically. Its quiet-running electric motors and isolated machinery made it difficult to pick up even when relatively close. Moreover, its ability to dive quickly and change depth confounded sonar operators. Sound waves refract differently at varying temperatures and pressures. The deeper the submarine went, the harder it became to maintain a consistent sonar contact. In effect, the Type 21 exploited a natural blind spot in Allied detection methods. Sonar could only see so far underwater, roughly a few thousand yards depending on conditions. A fast, deep-diving submarine could move beyond that range in minutes. And if it switched from a high-speed sprint to a slow, silent glide, even the most skilled sonar operator could lose track. It was like trying to catch a whisper in a hurricane. Allied intelligence had been aware that Germany was experimenting with new U-boats, but no one imagined a vessel that could cruise underwater indefinitely. It wasn't until captured blueprints and completed boats were examined in 1945 that the full scope of the innovation became clear. In one British intelligence report, an officer described the Type 21 as a submarine designed for the next war, not this one. To counter this invisible menace, Allied scientists began rethinking anti-submarine warfare entirely. Even before the war ended, research laboratories in the United States and Britain started studying ocean acoustics in greater detail. They learned that sound traveled differently in deep water layers, bouncing and bending through what became known as sound channels. These findings would later lead to the development of new sonar types, including passive sonar arrays that listened for the faint hum of submarines instead of actively pinging them. This shift from active to passive detection was a direct response to the lessons learned from the Type 21. But during the war, the Allies had no such systems ready. Their main countermeasures were still depth charges and sonar sweeps, tools designed for a different era of submarine warfare. And even these were becoming obsolete. A Type 21 could dive deeper than the effective range of most Allied depth charges, surviving explosions that would have destroyed older U-boats. Its improved hull strength allowed it to withstand pressures of up to 300 meters, whereas most Allied depth charges were set for shallower detonations. Some post-war tests even demonstrated that a Type 21 could survive near misses that would have crippled an American Gato-class submarine. The Allies did attempt to adapt on the fly. By 1945, escort groups began experimenting with new search patterns, broader sonar frequencies, and combinations of radar and acoustic data. They also increased the use of airborne MAD systems, which could detect the small distortions in Earth's magnetic field caused by a large metal object, like a submerged submarine. But even this had limits. The MAD sensor had to fly directly over the target, and its range was less than half a mile. Against a submarine that could change course and depth quickly, that was like finding a needle in a haystack.
Ironically, the most effective Allied weapon against the Type 21 wasn't a sonar or a radar. It was time. The war ended before the submarines could be produced in large enough numbers to make a difference. Germany managed to complete around 118 boats, but fewer than 20 ever left port, and only 2, U-2511 and U-3008, conducted operational patrols. Even then, both missions took place in the final days of the war, under strict orders not to engage unless attacked. The Allies never faced a full-scale campaign of these advanced submarines, and so their detection systems were never truly tested. After the war, that changed quickly. The U.S. Navy, British Royal Navy, and Soviet Navy all raced to seize as many of these submarines as possible. The Americans captured U-2513 and U-3008. The British took U-2518. The Soviets obtained several more. Each navy began an intensive study program, dissecting every system, from the propulsion units to the snorkel mechanism to the battery layout. American submariners who toured the captured boats were stunned by what they saw. Admiral Chester Nimitz, commander of the U.S. Pacific Fleet, reportedly commented that the Type 21 represented the foundation of modern submarine design. The Americans didn't waste time applying these lessons. The Guppy, Greater Underwater Propulsion Power program, in the late 1940s, took direct inspiration from the German design. U.S. submarines received streamlined hulls, enlarged battery banks, and snorkel systems, all derived from Type 21 technology. The result was a new generation of post-war submarines capable of sustained underwater operations. Similarly, The Soviets' Project 613 Whiskey class, and later the Project 641 Foxtrot class, were heavily based on Type 21 plans and engineering principles. Even Britain's first post-war submarines adopted the same concepts. In a sense, the Allies didn't defeat the Type 21, they absorbed it. Its technological DNA became the blueprint for every Cold War submarine that followed. From the American Skipjack class to the Soviet nuclear-powered designs of the 1950s, the echoes of the electroboat's innovation were everywhere. The age of surface-dependent submarines was over. The era of the true submersible had begun. But the legacy of the Type 21 went beyond engineering. It changed how navies thought about detection, stealth, and ocean warfare. The realization that sonar and radar could be outpaced by technological innovation spurred a global race in underwater acoustics, electronic warfare, and submarine detection. The United States launched massive oceanographic surveys to map sound channels, eventually leading to the Sound Surveillance System, SOSUS, a vast underwater listening network that stretched across the Atlantic and Pacific. SOSUS would later detect the quiet footsteps of Soviet submarines during the Cold War, a direct continuation of the challenge posed by the Type 21. The Allies' wartime failure to detect this German submarine also reshaped naval strategy. Submarines were no longer seen as defensive commerce raiders, but as strategic assets, capable of striking undetected anywhere on the globe. The Type 21 had proven the potential of the ocean's depths as a domain of stealth, where technology, not numbers, determined superiority. The United States and the Soviet Union both took that lesson to heart, investing heavily in undersea technologies that culminated in nuclear-powered submarines armed with ballistic missiles. The shadow of the Type 21 stretched far beyond the Atlantic. It became part of the logic of deterrence itself. If there is one irony in this story, it is that the Allies' greatest advantage, their massive industrial power, ultimately prevented them from realizing just how revolutionary the German design was until it was too late. They were winning, and victory often blinds. While Allied factories churned out thousands of Liberty ships, destroyers, and aircraft, German engineers were quietly inventing the future of naval warfare. In 1945, when American and British officers walked through the empty docks and saw those unfinished hulls, they must have felt both relief and unease. Relief that the war had ended before these machines could enter the Atlantic in force, and unease knowing that the next war might begin with them. The Allies couldn't detect the Type 21 because they weren't prepared to fight what it represented, a new kind of submarine, one that belonged to the next era, not the current one. It was faster than sound, quieter than sonar, and deeper than detection. Its true power wasn't just its speed or silence, it was the way it rendered entire categories of weapons and sensors obsolete. In the years after the war, as the oceans grew colder and quieter, that lesson lingered. The surface might belong to the victors, but the deep belonged to the unseen.